How's it going? I'm Rodrigo Aramburu. I'm the CEO of a company called BlazingDB, and for the last roughly 5 years, we've been working on a GPU-accelerated database management system. We actually started a big refactoring effort last year with a few different partners, and I'm going to talk about the open source ecosystem we've been working on to kind of create this reality of end-to-end analytics happening inside GPUs. We're going to be talking about a bunch of numbers that are dramatically smaller than what you were hearing in the last talk because we're really working on getting our single GPU algorithms really dialed in and then scaling it up. But we'll talk a little bit about how we've been scaling it up in the past few months, et cetera. So to kind of start out with, this is just to set the table. It's pretty obvious that GPUs are incredibly good at working on certain problems or certain workloads. So with machine learning workloads, with deep learning workloads, these are the reasons that GPUs are really being popularized outside of the video game or video editing sphere. And so what we want to see is there a way for us to do more than just machine learning and deep learning on these systems? So why GPUs kind of go a little bit further is GPUs are awesome. They're incredibly fast. This is from NVIDIA's CUDA programming guide, and it basically demonstrates the theoretical gigaflops that you can get off of an NVIDIA GPU versus what you would be able to get off of an Intel CPU. And beyond performance, the other thing is there's incredibly high bandwidth memory on all of these GPUs. So a single GPU, a Tesla V100, it'll have about 900 gigabytes a second of memory throughput from its memory to the CUDA processors, which are the processors on these GPUs. And it only takes 2 of these to start getting into the terabyte per second range. So when you can think about a server like a DGX2, this is an NVIDIA server. It's an 8U rack. It basically has 16 of these GPUs. So you're talking about incredibly high memory access. The only problem is GPUs suck. They have a bunch of different problems with them. One you can see is, all right, when we're talking about memory capacity, how much memory there is. A single GPU will have 32 gigabytes of memory. So yes, you have 900 gigabytes a second of throughput, but you only have 32 gigabytes. To get into the half terabyte range, that is an incredibly expensive box right there. So to even start scaling it up into this half a terabyte range, we're already spending quite a bit of money on quite a few GPUs. And then more importantly, the throughput to GPUs is behind the PCIe bus. And so any data that actually needs to get to the GPU has to go over PCIe, and that can be incredibly limiting as well. 12 gigabytes a second, or if you're talking about this server that I'm talking about, the DGX2, you'll have 4 of these. And so that's your effective throughput from system memory, for example, to the GPUs. So that really holds you back. And so one of the things that you see coming out of the GPU vendors, out of a bunch of different data center integrators, appliance builders, is there's hardware. There's hardware to solve all of these problems. So one of them is called NVLink or NVSwitch. This is effectively an interface or a connector between GPUs. And a switch can actually have 16 GPUs connected to it and be transferring 150 gigabyte per second of download and 150 gigabyte per second of upload. So incredibly fast interconnect between GPUs to other GPUs in a system. PCIe Gen 4 is starting to come out in a lot of different servers for high performance workloads. As we see more of that, we'll be doubling that PCIe bandwidth. And then a third one is GPU Direct, which basically lets you do remote device memory access between NVMe drives, SSDs, or other storage formats directly to the GPU. And so you can bypass operating system kernel calls, and you can literally just move data directly from where it's stored into the GPU. And the reason I'm trying to highlight this is all of these technologies have to be specifically coded for. Data centers can radically be different depending on what customer is doing what and how they're trying to do it. And so all of this just complicates things even further. So just a single, this is half right here of a DGX2 because they have 2 CPUs on them. So if I'm trying to move data let's say, from local NVMe drives. I'm going to have to go over that 12 gigabyte per second to the PCIe switch and then down to the GPUs themselves. If I want to do a shuffle between GPUs, I can use this NVLink, but then I have to code for that as well, right? And so it just gets increasingly complicated trying to build systems on these architectures to try to alleviate these I/O constraints. Because like we were saying at the beginning, GPUs have incredible computational performance capacity, but getting data onto the GPU is really, really quite complicated. And so all these different GPU analytics software providers, we're basically building all the same things, trying to figure out how to move data most effectively. And one of the things that I wanted to say is this is just half of one of these DGX servers, and you can put these as 2 of these, or you can even buy a rack now of 9 of what you're seeing here. So you can get incredibly dense racks of compute capability, but you're still really constrained by this I/O. So like I was saying, there's a lot of different GPU ecosystem vendors that are trying to build technologies off of this stack. And one of the things that we started realizing is we're building a lot of the same code. We're all building a good deal of the same code. So about 2 years ago, we got together, and to try to start playing nicer with each other, we created an interface where our systems could hand off to other systems very transparently and very performantly. And we did that by building Apache Arrow, but inside GPU memory. We call it a GPU data frame. And with this initiative, we started interconnecting our systems, but we really only used it as an interface. And that was kind of holding us back from the real potential of trying to actually build our systems cohesively and together. And so what happened is 3 of us, Anaconda, NVIDIA, and ourselves, came together and decided that we are going to invest heavily inside this technology, inside this GPU data frame, this Apache Arrow standard built on GPU memory, and try to actually push it forward with compute primitives that anyone and everyone can use. And so that ecosystem is called RAPIDS. So RAPIDS, or RAPIDS AI, is an open source ecosystem of a few different libraries, and it was launched in October of last year. We already have over 16,000 installs. We have 75 contributors. We represent about 10 of those contributors, and it's across the variety of the different projects. But there's a few different things that are really important inside the RAPIDS ecosystem. So one is the GPU data frame. So this is effectively this big purple bar here. The GPU data frame is just a columnar memory format inside GPU memory, and it's a lot denser than what Apache Arrow typically has. So Apache Arrow will typically have something like 4,000 records in a row batch. We'll typically have like 4 million records in a row batch. So we densify what we call a densification of what Apache Arrow is. And what the GPU data frame enables us to do is these different libraries, cuDF, cuML, cuGraph, all are interacting with the same object in memory, the same GPU data frame. And so cuDF basically enables us, or has all these GPU compute kernels, these primitives that I was talking about, that enable us to do data transformation on the GPU data frame. cuML is effectively scikit-learn, but GPU accelerated. cuGraph comes from UC Davis. It's a project from Gunrock, and it's basically graph analytics accelerated for the GPU. And what cuDF provides, it provides 2 different APIs. One is a high-level Python API, so that data scientists, those are the people that we're particularly targeting with this product, can interact with it with a pandas-like interface. The second API is a C++ API. And this is the one that we most extensively work with, because you can build products on top of the C++ API, and that's specifically what we did. And so taking these primitives that we've been building on GPU, we built a SQL engine on top of RAPIDS AI. And our entire premise is how can we connect raw files and enterprise data sources to this ML AI ecosystem. One of the ones that I wasn't mentioning, by the way, is cuDNN. cuDNN basically is the primitives for TensorFlow, PyTorch, Keras, a bunch of other deep learning frameworks that are incredibly popular. And so that's what we are. We are the SQL interface between this enterprise data and this machine learning, AI, GPU analytics ecosystem. So, oh yeah, I'll just show you real fast what that looks like, and then we can kind of go in, we can go a little bit further. So basically here I have a Jupyter notebook. The majority of our users interact through Jupyter notebooks, and what I've done is I've created a table. So I just made a context. I created a table off of a Parquet file, and I'm just going to run a query. But then what I'm going to do is I'm going to output that query into this GPU data frame. And because it's a shared memory object, there is a different library called cuDF that I was mentioning before that has a pandas-like API, and I can just run off of it as well. So what's happening is it's IPCing it between our engine and cuDF, and it's doing this in a zero-copy fashion. So it's literally just handing off the pointer for this particular thing. If I want to make it a little bit more complicated, here I'm going to be adding joins to my queries. And then what I can do is, because it's this shared Python object, I can grab this GDF, this GPU data frame, and I can create another table off of it as well. And then I can run another query off of that GPU data frame and output it. So it enables us in a Python ecosystem to have this kind of procedural SQL approach because we can hand it off between our process or cuDF, or we can hand it off now that we have it in this GPU data frame to cuML, that machine learning library I was talking about, or cuGraph, that graph analytics library that I was talking about. And so let me get back in here. And so let's talk a little bit about what the life of a query is in our architecture. So like I showed in the getting started real fast, there's a Python connector. We create a context, which is communicating with the BlazingSQL cluster. And what BlazingSQL then does is it'll receive that query. It'll send that query off to Apache Calcite. Apache Calcite is both our parser and our planner. We don't actually use the cost-based optimizer yet because we're not really sending it statistics. It's quite a naive implementation. But it parses out the plan and gives us a relational algebra tree. We then send that to our workers. So the RAL, that's what we call our relational algebra engine. And it basically has cuDF implemented inside of it. And that plan is converted into cuDF function calls. And then what happens is that'll then go to Rapids. So to talk about that a little bit further, whenever a query comes in, there will be Parquet files that'll be requested by the GPU. And what happens is we're able to do GPU decompression on the entire Apache or on the entire Parquet row group. So the gzip and snappy compression gets decompressed on the GPU, and then the actual columnar compression, whatever that happens to be, also gets decompressed in the GPU. And what this enables us to do is those things we were talking about with regards to GPU direct, for example, our ability to get things straight from storage and then into GPU, we're able to not go through the operating system kernel call, and it just enables us to have dramatically increased bandwidth. This is actually a new PR, so we don't have numbers off of this new version. We know that it's pretty fast, but I can't really get into what the numbers are because we're still talking about it. But we have been working on decompression. This is from a talk from our CTO as well as an NVIDIA CUDA engineer. And what we did is we took the TPCH data set, and this is actually part of a talk about how we do joins inside the GPU data frame, which is a really interesting talk. I can actually share the link for that. But what we did is we applied compression to the L order key. So this is just one of the order keys inside the TPCH dataset. And we applied cascading compression. So we can actually apply multiple compression schemas onto the same column. And what that enables us to do in this particular example, we did run length encoding, delta run length encoding, bit packing. And our decompression on the GPU was incredibly fast. We're getting 113 gigabyte a second decompression on the GPU of this particular column. And all of that is just because we were able to heavily compress it, and then the performance capabilities of the GPU lets us do decompression very quickly, and that's how we're able to increase the I/O, or the throughput to this particular system. Another thing that we do is we're implementing UCX. So this is us, this is Rapids, this is everything inside the Rapids ecosystem is basically utilizing this unified communication protocol, and it's built by a bunch of different network adapter providers as well as data center providers or tooling providers. And what it enables us to do is that data center topology that I was showing before, where we have to code for all these different interconnects. So we have to code for the NVLink, 150 gigabyte a second. We have to code for the NVMe. There's also work for RDMA from SSDs straight into GPUs as well. There's all sorts of different things that are happening right now. With UCX, we're basically able to code what these topologies look like, what these different connections between systems can look like, and then it manages CUDA IPC. That's an inter-process communication between two GPUs. It can manage RDMA InfiniBand between two networks or between two NICs. And so UCX is a standard that we've integrated into the Rapids ecosystem, whose sole function is really to make it so that data moves on the shortest path possible inside of this Rapids ecosystem that I was describing before. Another thing that we've been talking about is, so we get the data, right? We use UCX to transfer it wherever it is to the GPUs. We GPU decompress it to create a GPU data frame, and then we have to do things with it. So you can look at all this. This is on GitHub. These are all open source primitives. This is just a small fraction of them. I just wanted to list a few out to kind of show a little bit about what these primitives look like. But this is everything that we implement in the GPU for GPU compute, right? And as long as we have a GPU data frame, we can then apply these different primitives to be able to transform it into what it is that we're searching for our particular operation. Okay, and so this is where it gets pretty interesting. So what basically happens is we have this concept of a distributed GPU data frame. So on the BlazingSQL side, we'll execute a query. That query will then that query will then run. And what will happen is we will have a distributed GPU data frame that is deterministic, that is trying to split it across all the GPUs possible. And what is on the other side is Dask. So Dask was a project that Anaconda was pushing for quite a bit of time. Now one of the key contributors is actually at NVIDIA working on what's called the Dask GPU data frame. And what Dask does, it does a few different things. It's a distributed scheduler in a lot of ways. But one of the things it does is it has awareness of distributed arrays. They're called Dask arrays. And so what effectively happens is with a system like BlazingSQL, we create these GPU data frames and we shard these GPU data frames across a variety of GPUs. And what we then have is we have a list of tokens. These tokens are access to the GPU data frame in memory, and Dask workers are on the same GPUs, and they effectively can receive a zero-copy IPC. So they just receive the pointer in a way in a handshake, and they can then launch workers on that same GPU data frame that do something else. So really, something I'll show in a second is we basically did a data lake ETL process for feature engineering and then XGBoost. And Dask is the thing that picks up that data frame and then does the XGBoost workload, or the XGBoost workload on that GPU data frame. And so this is how we try to do our best to keep all the results in memory distributed as long as possible for an end-to-end workload to be accomplished. So really quickly, one of the things that we've been doing, by the way, so our project launched in November. We have 0.2 of our product out. We're working on 0.3, so it's still incredibly early days, right? We're talking about six or so months of work where it's actually been public. And we're doing these price parity comparisons. So it's very difficult to compare a GPU with a CPU architecture for a variety of different reasons. And so what we really focus on is, okay, we're gonna go on one cloud provider. They have total cost of ownership baked into that per hour compute of that device. And so we're going to just do price parity kind of comparisons. So for this one, what's happening is we're looking at this mortgage workload, and this is data from Fannie Mae. It's about 148 million performance records. These are just records of loan performance. and we're going to do this feature engineering process that I was talking about. We're not going to run it because it's just a lot of different things, but I'm going to pull it up just to kind of show real fast. So basically what's happening is we're bringing in all these different files, and once we bring those different files in, we're just doing a whole heap of queries. And this whole workflow is running, and then once the features are engineered, then we'll launch an XGBoost job that'll then do the training on it. And so for this particular example, at price parity, just one Tesla T4, this is a very small 95-cent an hour GPU, we were able to get close to 20 or around 20x performance improvements with a price parity Spark cluster. Again, we're only talking 16 gigs of data on the higher end, so it's a pretty small problem. One of the things that we did is, how do we scale this up? So NVIDIA gave us access to a DGX1. This is basically a 4 GPU cluster, and what we did, because our engine is still single node right now, that'll be changing in the next few weeks, we actually created a Dask worker around BlazingSQL nodes, and we launched it on 4 GPUs simultaneously, each doing different portions of the problem because the problem just could lend itself to being split up like that. And so on this DGX, we used Dask to split up our workloads and then receive the result sets and then run XGBoost. And for about 192 gigs, we were able to run the whole thing in about 400 seconds. There's 100 CPU Spark node that NVIDIA tested against. We haven't done our own price parity performance comparison with this one, just because we haven't had time to. This came out last week, but NVIDIA had like a 100 CPU Spark cluster running the same exact workload over the same exact scale of data, and they were getting over 3,000 seconds for the same type of workload. So this is just one of the ways that we've cut around distributed and tried to just show how we could start distributing things, although that's going to change as our engine is actually managing it, managing the shuffle, trying to leverage CUDA IPC, all these kind of cool technologies I was talking about behind UCX. But this is how we did with almost 200 gigs of data. So another quick demo, actually. So this is network traffic analysis. So Graphistry was one of the companies that I mentioned when I was talking about the GPU Open Analytics Initiative. And what they effectively do is they do graph visualization, and it's GPU accelerated to be able to render 4 million nodes plus kind of opportunities for their customers. And they do it all inside of a web app. And so what we did with them is they had this network traffic problem for one of their customers that's trying to detect anomalous activity in network traffic. But you can think about this as just like any log data. So we have 65 million events. We have them in a Parquet file. And what we basically have to do is we just have to run this SQL query on top of those 65 million events. So what we run that query, we get these events, and then all I have to do is send over the data frame to a tool like Graphistry, and we can render that network in real time. And now we can start looking at this network, and that was done really quite quickly, right? This query ran in about a second. Again, this is because of the high bandwidth memory that GPUs afford you. So yeah, it's about 5 gigs of data inside the GPU, and then we just transform it really quickly with all that GDF stuff I was talking about. And then we can render it here, and we can start looking through this particular network and look for anomalous activity. I don't want us to necessarily get too much in the weeds of that, so we will come back to this. We did another price parity comparison. It's the same exact cluster that I was talking about for the XGBoost workload, so 4 Spark nodes with 8 vCPUs versus 1 Tesla T4 GPU. And with this one, we got almost 100x performance improvement on the actual ETL phase. So this is the actual transformation phase. Our loading was roughly about the same, was a little bit faster than Spark. That'll change really soon with that new Parquet PR I was talking about, which does all decompression on the GPU, which will dramatically accelerate our ability to be able to load files from Parquet into GPU. But again, these are the kind of opportunities that GPU acceleration enables, right? Price parity, but 100 times faster. Almost 100 times faster. So one of the things I've been alluding to is, yeah, it's a very new technology. Rapids is incredibly new. It launched in October. There's already over 1,000 issues that have been submitted. I'm sure there will be a good deal more over the next year. There's a lot of work to do. We're not even going to call it 0.1 till our best bet is late 2020, or 1.0 until late 2020. But we are trying to release as quickly as possible. So one of the things that we're going to be supporting, and this is supposed to happen any day now, is strings. So GPU string support is actually very complicated, especially if you're trying to do substring search. Just the way that GPUs are programmed for, it just makes it really complicated to support strings. We just got that into the Rapids ecosystem, and we'll be integrating that into BlazingSQL any day now. Hopefully it'll be out before the end of this week. The next thing that's actually very close, we're really far along, is our distributed scheduler. So everything I've been showing you, data all has to fit in GPU memory right now. Whatever we decompress the Parquet files or what have you, it all has to fit inside these GPU data frames. With our distributed scheduler, we'll be able to attach more GPUs and then have this distributed GPU data frame functional over much larger memory footprints. And so that we actually think will be out in about, we have a customer that we promised it to in about 3 weeks, so it should be out hopefully in less than 3 weeks. And then finally, or not finally, but the next one, it's our physical plan optimizer. This is basically data skipping. So Apache Parquet, the metadata, awareness of that metadata means that we can start planning out our I/O reads more intelligently, and we can also skip a great deal of row groups depending on the query. And it'll also enable us to just be bringing in the particular Parquet columns that we need, as opposed to bringing in, right now we decompress the entire row group into GPU memory. And so when you're running a query, like the query I was showing off for this particular demo, we only needed half the columns. So that's another way that we'll be able to start scaling it up pretty aggressively. The versions that aren't listed here, but we're starting to plan out and roadmap out, are things like cascading off of GPU memory into local system memory, cascading out of local system memory into local drives. There's a whole heap of different things that we really want to do very soon. But yeah, this is what's going to have us busy for the next 2 to 3 months. So yeah, this is all available. So you can actually get Rapids. You can get the Rapids containers off of Docker Hub. You can also do conda install, pip install of the Rapids work. For us, we only support Docker Hub and conda install right now, but it's very easy. You can get up and running. Like I showed in the getting started, you basically point it to a file, and then you can query that file, and you can start running, and it's entirely in GPU memory. If you're trying to do any AI workloads or ML workloads that could benefit from GPU acceleration, then this is probably like the easiest way to get up and running with Python in this ecosystem. So we definitely recommend it. And that is all. Thank you very much.